Hello, Tech Unplugged, and welcome to another deep dive.
Yeah, hey.
We've got some really interesting stuff to dig into today.
Absolutely some really fascinating stuff.
It all centers around Windows APIs.
Yeah. You know those like core building blocks of how Windows works and
Right, like under the hood stuff that we don't always think about.
exactly, but they're so important for everything from, the apps we use every day to like,
To the whole world of cybersecurity.
oh yeah, for sure.
We're going to see how they play a role in both building software and kind of breaking it down too.
That's right. We'll even touch on how these concepts from the Windows world.
Can relate to like totally different fields.
Yeah, some surprising connections there.
So get ready for some serious aha moments as we unpack all of this together.
Okay, let's jump in. So we're talking Windows APIs.
Yeah. What exactly are they if you had to explain it to someone who had never heard of them before?
Well, think of them like this. They're the essential toolkit that Windows provides,
Okay.
so that any piece of software can basically ask the operating system to do things for it.
So instead of every single application needing to know,
Yeah.
like all the complicated details of how to manage a window,
Right, or save a file.
connect to the internet.
Exactly. They
Wow.
can just use these pre-built functions that Windows provides.
Like a set of standardized commands.
Exactly. It's like a universal language for software to talk to the operating system.
So it's making things much more efficient.
Absolutely.
Yeah.
It's like instead of reinventing the wheel every time,
Right.
you've got this shared set of tools.
Okay. Now we've got all this information about different versions of APIs, like
Right.
Win16, Win32, Win64, WinC. What is the deal with all these different flavors?
Well, this is actually really cool because it kind of mirrors the evolution of Windows itself.
Oh, interesting.
So, Win16, that was back in the day of those older 16-bit versions of Windows.
Yeah.
Then along came 32-bit systems, and we got Win32 offering more power, more features.
Makes sense.
And today, of course, we've got 64-bit Windows using Win64 for even more memory and performance.
And what about that WinC? I've seen that mentioned.
WinC. That was kind of a specialized version designed for those, like, embedded systems.
Oh, right, like in devices and things.
Yeah, exactly.
Yeah.
So the main takeaway here is each API version is tied to a specific architecture of the Windows operating system.
So if I dug up an old program that was made for Win16, it might not just run on my modern computer.
You're exactly right. While Windows tries to maintain some backwards compatibility,
Okay.
those older APIs might not work perfectly or even at all on a newer system.
Got it. So developers really have to think about what version of Windows they're targeting.
Exactly. And that's where the Windows SDK comes in.
SDK.
Yeah, the software development kit. Think of it like this. It's the ultimate resource library for anyone who wants to build Windows applications.
Oh, okay. So it's got all the instructions and tools you need.
Exactly. It's got the documentation, the code libraries, the tools, everything a developer needs.
So it's like the master guide for speaking the Windows language.
You got it.
But wait a minute, I've also seen this stuff about MFC, ATL, WTL.NET, Java.
Yeah.
These all sound like different languages.
Well, they kind of are, but they're actually built on top of the core Windows API.
So they're like higher level tools.
Exactly. They give developers a more convenient way to work with the API,
Okay.
often using object-oriented programming.
Yeah.
So instead of writing tons of low-level code,
Oh, I see.
they can use these frameworks to build things faster and more efficiently.
Like pre-built construction kits for software.
Exactly.
All right, so we've talked about the different API versions and these higher level frameworks.
Right.
But what about the actual nitty-gritty of how a Windows program works? We've seen WinMain and WendyProc mentioned a lot.
Okay, now we're getting to the heart of it.
Yeah.
So if you're looking at a basic C or C++ program for Windows,
Okay.
WinMain is like its starting point.
Mm-hmm.
It's kind of equivalent to the main function you see in other programs.
I see.
But there's a big difference. Windows programs are event-driven.
What does that mean?
It means they're constantly responding to things that happen like user input or system messages.
Okay.
And that's where WendyProc comes in. That stands for Window Procedure.
Window procedure.
It's a function that the developer defines to handle all these different events or messages.
So, like, what kind of messages are we talking about here?
Well, just about anything you can think of that could happen in a window.
Okay.
Like when the window is first created,
Uh-huh.
when you resize it, when you click the mouse, when you type on the keyboard.
So WinMain sets things up, and WendyProc handles the events.
Exactly. WinMain's main job is to set up that main window for your application.
Okay.
And it does this by registering a window class, which basically defines the characteristics of the window.
And then actually creating the window on the screen.
You got it. And then WendyProc is where the developer gets to define exactly how the application should respond to each of those events.
So inside OneUProc, you'll have code that says, if this message happens, then do this.
Exactly. Often it's structured as a switch statement that examines the message type.
Okay.
And based on that message, it executes the appropriate code.
So if the message is WMSI, meaning the window has been resized, then OneUProc might contain code to redraw the window's content to fit the new size.
Exactly. Or if it's WMLBED and down N, which means the left mouse button has been clicked, you can trigger some specific action. Or maybe even display a message box using the message box API.
Oh, okay. So even a super simple program that just shows a message box still relies on this WinMain and OneUProc structure.
Absolutely. Even the most complex applications with tons of features all build on this same core model.
It's like the foundation of any Windows program.
Exactly. And there's this thing called the message loop that runs inside WinMain.
Message loop.
It's this constant cycle of checking for new messages, translating them, and dispatching them to the WinUProc.
So it's what keeps the application alive and responsive.
You got it. It's constantly looking for those events and making sure they're handled.
Okay, so now we have a pretty good grasp of how Windows programs are structured.
Yeah.
But what about how they actually display stuff on the screen? This concept of a device context seems really important here.
It is. It's a fundamental concept in Windows graphics.
So what is it exactly?
Well, think of it as handle a connection to a specific output device.
Okay.
This could be your monitor, your printer, even a section of memory.
Okay.
It provides a way for your program to draw graphics and text without needing to know all the low-level details of the hardware.
So it's like a universal canvas.
Exactly.
My program can draw on, and Windows takes care of translating those drawings to whatever device is connected.
That's a perfect way to put it. So when you want to display something, you first get a device context for your window using the getDC function.
getDC.
Then you can set things like the font you want to use by calling select object.
Okay.
And to actually draw text, you might use a function like textOut, which will let you specify the coordinates, the text, and its length.
And when you're done drawing,
you call release DC to give the device context back to the system.
Right, so other applications can use it.
Exactly. Now, how does a program know when it needs to redraw something, like when you resize the window?
Right, that's a good question.
Well, remember those messages we talked about?
Yeah.
There's a specific message called WMSIZE that gets sent when the window size changes.
Okay.
And your WinDproc can handle this message by getting a new device context and redrawing everything to fit.
So the messages tell the application when to do something, and the device context provides the tools to actually show it?
Exactly. They work together to make everything happen.
Okay, so we've covered a lot of ground here.
We have.
We've seen how Windows programs are structured, how they handle events, and how they display graphics. But now let's shift gears a bit and talk about Windows APIs and cybersecurity, specifically red teaming.
All right, so now we're getting into the more adversarial uses of these tools.
Exactly. It's kind of the flip side of the coin, right?
It is, because Windows APIs give you such deep access to the operating system.
Okay.
They're incredibly valuable for things like penetration testing, red team operations, and even malware analysis.
So security professionals use them to find vulnerabilities.
Right, and also to understand how attackers might exploit them.
And how does that work exactly?
Well, these APIs provide the low-level access needed for some pretty advanced techniques.
Like what kind of techniques?
We're talking about things like reading the memory of other processes.
Which could be used to steal information.
Exactly. Or executing code with elevated privileges to gain more control over the system.
So basically becoming an administrator.
Right. Then there's system enumeration, which is all about gathering information about the target environment.
Like what software is installed, what users are logged in.
Exactly. And then there are techniques for potentially disabling or bypassing antivirus software.
Wow. So the same tools used to build software can be used to undermine its security.
It's a double-edged sword, for sure.
That's kind of unsettling.
It is. But it's important to understand both sides of it.
Absolutely. Now, you've shared some information about specific Windows APIs and how they're used in security.
Right.
Let's dig into some of the more notable examples.
Okay, we'll take Create ToolHelp 32 Snapshot, for instance.
Create ToolHelp 32 Snapshot.
It's not specifically a security function, but it lets you take a snapshot of all the processes and modules running on the system.
Okay, so an attacker could use this to see what's running on a target machine.
Exactly. It's like a reconnaissance tool.
I see. And then there's Open Process.
Right. That one lets you get a handle to an existing process which is essential for interacting with it.
And once you have that handle,
You can use get module file name XA to find the exact location of the executable file on disk.
so they work together to give you a complete picture of what's running and where it's located.
Precisely.
What other APIs are important in this context?
Well, shell execute-x can be used to launch external applications.
Which an attacker could use to run their own malicious programs.
Right, and to understand the security context of a process.
Okay.
They might use get token information, which reveals things like the process's privileges and the groups it belongs to.
And if they want to gain more privileges,
They might try to use adjust token privileges to enable certain rights within their access token.
so it's all about escalating their level of access.
Exactly.
It's interesting how the names of these APIs often tell you exactly what they do.
It's true. They're usually pretty descriptive.
Now, what about those APIs for directly manipulating processes?
Oh, yeah. Those are some powerful ones.
Hmm.
We've got read process memory and write process memory.
Which do exactly what their name suggests.
They do. They let you read from and write to the memory of another process.
And this is crucial for code injection, right?
Absolutely. That's where you inject malicious code into a legitimate process so it gets executed.
And virtual Alex lets you allocate memory within another process.
Right. Virtual ProtectX lets you change the protection attributes of that memory.
So you could mark a region of memory as executable after you've injected your pod.
Exactly. And then there's create a remote thread.
That one sounds particularly scary.
Yeah, it's a key API for code injection. It lets you create a new thread of execution within another process. And you can point that new thread to your malicious code.
So it runs within the context of that legitimate process.
Right, which makes it much harder to detect.
And what about open process token, get probe address, and create process?
Well, open process token lets you get a handle to a process's security token. Get pro address lets you find the memory address of a specific function in a DLL. And create process-C lets you create entirely new processes.
So it's all about gaining control over the system and running your own code.
Exactly.
And what about duplicate handle and get current process?
Duplicate handle lets you create copies of important system handles. And get current process gives you a handle to your own process.
And open thread, get thread context, set thread context.
Those are for manipulating individual threads within other processes.
So you can really get down to a granular level of control.
You can. And then there's queue user APC.
Queue user APC.
This one lets you queue a function to be executed by a specific thread later on.
Wow, it's amazing how many different ways there are to interact with processes.
It is.
Mm-hmm.
And even something as simple as message box A, which just displays a message box,
Right.
can be used for malicious purposes like showing fake error messages.
Oh, wow. So even the seemingly innocent APIs can be dangerous.
Exactly. You have to be aware of the potential for misuse.
And you mentioned hooking techniques like set Windows HookX.
Oh, yeah. Those are powerful but complex.
What do they allow you to do?
Well, they let you essentially intercept and potentially modify the behavior of other API functions.
So you could change what happens when someone calls message box A, for example?
Exactly. You could display a different message or log the fact that it was called.
That's really interesting.
It is. It opens up a lot of possibilities for both good and bad.
Okay, so we've seen how Windows APIs are fundamental for building software, but also how they can be used for both offensive and defensive purposes in cybersecurity.
Right.
Now let's dive into the import address table, or IAT.
Okay, the IAT is a crucial part of how Windows executables work.
So what is it exactly?
Well, it's basically a table within an executable file that manages calls to functions that are located in external DLLs.
DLLs?
Yeah, dynamic link libraries. They're like separate modules of code that can be shared by multiple programs.
Okay.
So when your program needs to use a function that's in a DLL, it doesn't know the exact memory address of that function beforehand.
Right.
So it looks it up in the IAT.
So it's like a directory of function addresses.
Exactly. And when the program is loaded into memory, the Windows loader resolves those addresses and fills them in the IAT.
So this allows for dynamic linking.
Right, which means DLLs can be updated independently without breaking the programs that use them.
That's really clever.
It is, but it also introduces a security risk.
How so?
Well, because the IAT contains those actual memory addresses, an attacker could potentially modify them.
Oh, I see. So they could redirect a function call to their own malicious code.
Exactly. So instead of calling the real message box A function, it could end up calling the attacker's code.
That's a sneaky way to hijack the program.
It is, and it can be very difficult to detect.
Are there tools for inspecting the IAT?
Yes, there are tools like pview that let you see the internal structure of executable files, including the IAT.
So you can see which DLLs a program uses and what functions it imports.
Exactly. And there are Python libraries like pfile that give you programmatic access to this information.
So security analysts can automate their analysis.
Exactly.
Now, what about IAT manipulation and evasion techniques?
Oh, yeah, that's a whole other level of complexity.
What kind of things do attackers do?
Well, one common technique is using ordinals instead of function names when importing from DLLs.
Ordinals.
Yeah, they're basically numerical identifiers for functions.
Okay.
So instead of importing message box A by name, they might import it by its ordinal number.
Which makes it harder to understand what the code is doing.
Exactly. It obfuscates the API calls.
And what about direct syscalls?
Ah, those are even more stealthy.
How so?
Well, instead of going through the normal Windows API functions, they directly invoke system calls, which bypass a lot of security checks.
So it's like going straight to the kernel.
Exactly. It's a much lower level way of interacting with the operating system.
That's pretty impressive.
It is. And then there's IAT hooking itself.
Right, we talked about that earlier.
It's a powerful technique for redirecting API calls.
And attackers also use techniques to hide the IAT altogether.
They do. It's all about evading detection.
And what about the defenses?
Well, there are things like runtime behavior monitoring, which looks for suspicious patterns.
Okay.
And IAT integrity checking, which tries to detect modifications.
And anti-hooking techniques.
Right. It's a constant arms race between attackers and defenders.
It sounds like it.
It is.
Now, you mentioned an example of working with ordinals, specifically with message box A.
Yeah, this is a good way to illustrate how ordinals can obscure things.
So how does it work?
Well, message box A has an ordinal number, which I believe is 2150.
2150.
So instead of calling it by name in your code, you can load user32.dlol using load library, and then get the address of message box A using getProc_address, but instead of passing the name, you pass the ordinal number.
So it would look something like getProc_address with hmodule and 2150 as arguments.
Exactly.
Yeah.
And this makes it much harder to tell what the code is doing just by looking at it.
That's pretty clever.
It is. And for even more stealth,
Yeah.
attackers might avoid calling load library directly or even implement their own syscalls.
Wow, so they're going to great lengths to hide their tracks.
They are. And they also use techniques like string and code
obfuscation.
Yeah, like encrypting the strings in their code so they're not visible in plain text.
That makes analysis even harder.
It does.
Yeah.
And then there are techniques like anti-debugging and sandbox detection.
Which make it harder to analyze the code in a safe environment.
Exactly. It's all about making the analyst's job as difficult as possible.
Now let's switch gears again and talk about how C# developers can use Win32 APIs through Invoke.
Invoke. It's a powerful tool.
What does this stand for again?
Platform Invocation Services.
Platform Invocation Services.
It lets you call unmanaged code for managed code.
Okay. Unmanaged versus managed.
So unmanaged code is like your classic C or C++ code that interacts directly with the operating system. While managed code like C# is run by the .NET framework, which provides a lot of safety and security features.
I see.
But sometimes you need to access those low-level features that are only available through unmanaged code.
And that's where Invoke comes in.
Exactly. It acts as a bridge between those two worlds.
So if I'm writing a C# application and I want to use message box A,
you can use Invoke to call it.
How does that work?
Well, you basically create C# declarations that describe the native API function you want to call.
Okay.
And then Invoke handles all the messy details of data type conversions and calling conventions.
So it's like a translator between C# and the Win32 API.
That's a good way to put it.
Finally, let's talk about red teaming large language models.
This is where things get really interesting.
Yeah, it seems like a completely different topic at first glance.
It does. But the underlying principle of red teaming is the same.
Which is?
Proactively trying to find weaknesses and vulnerabilities.
But instead of looking for exploitable API calls, you're trying to get the LLM to produce harmful or undesirable outputs.
Exactly. It's called RAI, red teaming. Responsible AI. It's all about making sure these powerful models are used safely and ethically.
So how does it work in practice?
Well, it involves assembling a team of red teamers who have a wide range of expertise and perspectives.
I see.
And they try to elicit problematic behavior from the LLM using various techniques.
Like what kind of techniques?
Well, it could be anything from open-ended exploration to more targeted prompts based on known harm categories.
So they're basically trying to break the LLM.
In a controlled environment, of course.
Right. To see what it's capable of?
Exactly. And to identify any weaknesses in its safety mechanisms.
And then this information is used to improve the model.
Exactly. It's all about making these models more robust and reliable.
So it's similar to red teaming in cybersecurity.
It's just applied to a different domain.
It's fascinating.
Yes.
Well, this has been a really comprehensive deep dive into the world of Windows APIs.
It has.
We've covered a lot of ground from their fundamental role in how Windows works
Right.
to their importance in both software development and cybersecurity.
And even red teaming LLMs.
It's really amazing how much these APIs influence our digital lives.
They really do. They're everywhere.
And understanding them gives us a much deeper appreciation for how complex and powerful these systems are. So as you can see, the Windows API is a vast and intricate landscape, fundamental to how Windows operates, and a critical area for both software development and cybersecurity. From the basic building blocks of creating a window to the sophisticated techniques used in red teaming and malware analysis, understanding these APIs unlocks a deeper appreciation for the power and complexity of the Windows operating system. The ability to interact with the system at this level provides immense control and insight. We hope this deep dive has shed light on the significance of Windows APIs and sparked your curiosity to explore further. Thank you for listening, Tech Unplugged. Stay tuned for more deep dives.